All right, folks, we're going to start this section 9.1. It's really section-wise. In this chapter, I've got it all kind of messed up. So we're not going to do, I think there's 6 sections in this chapter, 7. I'm going to do 9.1 and 9.2 today. Briefly, it won't take very long to get through both those sections. Then we'll do rotations and dilations together. And I'll briefly then talk about compositions on top of that. So we may very well like wrap this chapter up in 2.5 sessions. But transformations are collectively the terms that we use, the movements that we conduct on shapes. Okay, what's important to understand is that we're going to do this not only in shapes and geometry in this course, but this becomes one of the most important things that we do with parabolas and other functions in Algebra 2 and College Algebra. It's actually, at least teaching College Algebra, it's a good portion of that class. I would say we talk about transformations at least probably 80% of the time in that class. And I just finished talking about it in trig as well, with trig functions. So it's something that is very pivotal for us to pick up and understand. Obviously, we're going to do it with shapes here, but everything we do with shapes will then translate to functions. So you guys did this. If I take this shape right here and I want to move it down 2 units into the right 3 units, so there's down 2, and then 1, 2, 3 units to the right, and we just did what we call a translation. You might have talked about them called slides or shifts or something like that, but we went from that shape there, and look at the ordered pairs, to that one. Okay, and if I look at the order pair, so I went down 2. So right now I go 5, 3, 1. When I go down 2, that should take that to a 3, that to a 2, that to a -1. If I do that, 3, what did I do? Yeah, gotta go subtract. So I'm going down 2. So 3, 1, -1. And that's what we've got. Okay. Then I said I'm going to move right 3. So when I move right 3, moving to the right is addition, so that's going to become -2. That'll be -5, and that will be a +1. Okay. So you see, all we're doing here when we translate something, we are adding or subtracting to the x's and to the y's. And when I shifted this, I was just kind of focused on A at the moment, so I moved A 2 units down and then 3 units to the right. And when I do that, because A and B were stuck together at the beginning with a definitive distance, a definitive edge here, then when A transfers and moves, B is going to transfer and move in the same way, and so is C. Okay, so that logic there is kind of what we get when we start talking about these what we call rigid motions. Okay, a rigid motion is the action of taking an object and moving it to a different location without altering its shape or size. Okay, so what that means to us is that shape right there, if we look at all the distances and angles and all that kind of stuff, so there's my angles. When I move it around, the angles still stay the same, right? Okay, if I look at the distances, so I'm just going to look at these distances here. So these are the 3 segments of that triangle. When I move the triangle, those 3 distances stay the same. Okay. So what that means is that shape right there that I started with, and that shape right there that I finish with, or wherever I move it to, wherever I finish it, the 2 shapes are still congruent. Okay. So that's a unique thing with what we call rigid motions. A lot of times rigid motions are called isometries. Okay, so an isometry is essentially a movement that preserves distance, which means distances don't change. Okay, so you might see the word rigid motion. You might see them called isometries. They're really synonyms for us. Reflections, rotations, and translations are all rigid motions. Okay, or they're all isometries. Just some language here. The pre-image is the picture that I started with. Before I did anything to it, before I did any movement, the picture I started with was the pre-image, and the picture that I get when I'm done is called the image. Okay, so translation is often referred to as a slide. You simply take the pre-image and slide each ordered pair of the image in an X direction, then a Y direction. So the notation can be shown using ordered pairs, like it is referred to as a mapping, and looks like this. Okay, so say your X value of your pre. So this is the X values of my pre-image, and these would be then how I generate the X and Y values of my image. So it's saying your X value, whatever your X value of your pre-image is, you're going to add 2 to it to get your image. Whatever your Y value is of your pre-image, you're going to subtract 4 from it to get your image. Okay, so that's one way you're going to see the notation. This notation means the same thing, and they vary back and forth. Some questions will incorporate that. Some questions will incorporate this. This is still your X value. Okay, this is referring to your Y value, and because that number is positive, it's telling you essentially add 2 to whatever your X is, and because that number is negative, it's saying subtract 4 from whatever your Y is. So these two notations, those two notations are identical in regards to what they do to our image. Okay, so this one here, all I want to do, I'm going to start with this ABCD, this polygon, quadrilateral. And let's go ahead and take ABCD and translate it. Let's do this. Let's write it this way. Let's go X comma Y and go X. Let's go plus 3 Y minus 4. Okay. So what I want to do here real quick, just kind of give you the graphical application here. So every X value is going to go to the right 3 units. So 1, 2, 3, and it's going to go right there. And then this one's going to go 1, 2, 3 to right there. That one goes 1, 2, 3 to there. And then 1, 2, 3 to there. So that was moving everything to the right 3 units. Now, the minus 4 is going to be the fact that once B is moved to the right 3, you're now going to go 1, 2, 3, 4 down, and that point right there will become B prime. D is going to move 1, 2, 3, 4 down. It'll go right there and become D prime. Same thing with C, 1, 2, 3, 4. C becomes C prime. And then A, 1, 2, 3, 4. And now we got A prime. If I connect those, so I've got A to B, or A prime to B prime. We get B prime to go to D prime to C prime, and then C prime to A prime. You can see that that green shape is the same, it's congruent to the original. Okay. Now, often what we're interested in is not necessarily what the shape is, but what these ordered pairs are. So this ordered pair here, C prime, is located at 1, 1. D is at 2, 1, 2, 3, 4. So 2, 4. B prime is at negative 1, 2, 3, and then 1, 2, 3, 4, 5. So this one's at negative 3, 5, and this one here, A prime is at negative 3, negative 4, negative 5, So x is -5, y is 1, 2, 3, -5, -3. All right, so that's kind of nuts and bolts of that. But let's go back to looking just briefly. Kind of clean this up a little bit. Remember, this was B prime. If I look at the original B, it's located at 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9. So -6, comma 9. A was at then, that would be -8, comma 1. D is at -1, comma 8. And C is going to be at -2, comma 1, 2, 3, 4, 5. And all I want to do here real quick is just kind of focus on that point there, which was B, and this one here of B prime, which is at -3, 5. If I look at those, how do they relate? Well, take this -6 and add that 3 to it. You get the -3 right here. Take this 9, subtract that 4 from it, and you get your 5 for B prime. And that pattern should be the same no matter what. Okay, so if I start at D and go to D prime, add 3 to -1, and it gives me that 2. Subtract 4 from that 8, and it gives me that 4. Let's go from C, which is that point, to C prime. Add 3 to -2, and it gives you your 1 here. Subtract 4 from 5, and it gives you that 1 there. So I think what we're seeing here is that instead of actually spending the time to move these and actually pick this blue one up and transfer it so it becomes the green one, is to actually just look at the ordered pairs, do the algebra to the ordered pairs, and then that gives us essentially A prime, B prime, C prime, and D prime. Often they'll ask you, okay, what is the transformation that's being taken place here? So usually, this will be my pre-image, and this is my image. Generally speaking, when the prime notation is telling you what your image is. So I'm just going to look to see what C to C prime is. So it went to the right 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so my X value increased by 9, and then my Y value is going to go down 1, 2, 3, 4, 5, 6. So my Y value decreased by 6. So I would write my mapping this way. Or I would write it this way. I would say T for translation. And then I put these are actually vector notation. I want to talk about vectors in trigonometry. Maybe a little bit towards the end of the year if we have time. But that +9, so this is going to just be a +9 there. And then I go follow it up by a comma. And then this is -6, so -6. And then I close it off with that kind of angle, parenthesis angle bracket, but that's later on you're going to find out that's vector notation. All right, so that's a translation. Hopefully that was not something that was all that new to you. Okay, reflections shouldn't be new either. Okay, so inside reflections, distance is always preserved, so distance is saved. So it's isometry again, distance is saved. So when you reflect over a given line, the distance that the original point was in the pre-image to the point that is now on the image, that distance should be the same. Okay. So you can complete reflection across any line you wish. So the most common lines of reflection are the x-axis, y-axis, the lines y equals x and line y equals -x. Okay. And this is the idea that this is just kind of demonstrating the distance is preserved idea that, you know, this distance right here, this little green distance, let's call that point A, is from my line of reflection, is going to be the same as that distance right there for A prime. And the same thing happens down here on the red and the blue. And even if I put a point right there and figure out that distance there, then it should end up being the same to right there. Okay. So we call this a horizontal reflection because the image actually moves left to right. So left to right movements are horizontal. This one here is called a vertical reflection because the image starts at the top and it moves down. So that's a vertical alignment or vertical movement. Kind of show you what happens here when we take A and reflect it over the x-axis. Remember, this is x-axis. A, distance is preserved, so that distance right there is a distance of 2 units. So when it reflects over the x-axis, it should go right there, and that should be A prime. So now when I think about what the ordered pair for A is, it'd be negative 1, 2, 3, 4, 5, 6, comma 2. So negative 6, comma 2. Well, if I look at A prime, that's going to be negative 6, comma negative 2, because now I went down instead of up. Okay. Look at B. B is located at 1, comma 8. Okay. So that distance right there, which is 8 units, needs to be reflected and become 1, 2, 3, 4, 5, 6, 7, 8. So there's B prime. And if I count, that'd be 1 to the right, down 8. And then this C is 1, 2, 3, 4 units. So 1, 2, 3, 4 there. And I get C prime. If I connect these things, okay, I'm not very good at sketching with this tablet, but you can roughly see that that triangle would be the same or congruent to the one we started with. Now if I look at these ordered pairs, I believe that one is a 6. I guess this would be 6, comma 4, and this is 6, comma negative 4. If I compare the ordered pairs for A prime and A, they are the same thing, except for the Y and A prime is opposite. If I look at these two, they are the same, except for the Y is opposite. And then if I look at that one and that one, they're the same ordered pair, but again, the Y is opposite. So what does that mean to me? It means if I have X comma Y on my pre-image, then I'm going to have X comma the opposite of Y on my image when we do an x-axis reflection. Okay, so all that happens for every point is that your Y value becomes the opposite, and that's what actually flips it over the x-axis. Now you can use x's and y's. I prefer a lot of times to say if the ordered pair A comma B is on my pre-image, then when I do an x-axis reflection, the point A comma opposite of B is on my image. I like to stay away from x's and y's. It gets a little confusing for people. I'm going to use A and B a lot of time, but know that A, obviously it's the first coordinate here, so is an x coordinate. B is a y coordinate. And this just says then, well, in the image, then the x's of the pre-image and image are the same. This says that the y values of your image and pre-image are just opposite one another. So that's how we reflect over an x-axis. Okay, so a similar thing happens when we reflect over the y-axis. Reflecting over the y-axis, so let's just look at A here. It is, what, 6 units to the right, 1, 2, 3, 4, 5, 6 units to the right, 3 units down. So that's 6, comma 3. If I reflect over the y-axis, remember that's your y-axis, distance is preserved, so I need to have that distance right there is going to be repeated over here. 1, 2, 3, 4, 5, 6. And I'll have A prime right there. Well, what direction did I go? I went left, so that should be negative 6. The y value is still negative 3. I didn't put my negative here. Okay. If I look at B, B is at 4, 3. But when I reflect it, it should go over here to B prime, which is going to be negative 4, 3. And then C right now is at 10 comma 7. It's going to go to negative 10 comma 7. And that will be C prime. And we connect them. Again, you see, you get the same shape. But let's compare the ordered pairs. How are these two ordered pairs comparable? How do these two compare? And then how do A and A prime compare? Well, if we think about it, the idea is if it was an x, and so if A is my x coordinate and B is my y coordinate, on my pre-image, what do I get on my image? Well, on my image, I'm going to get, if I look at it, what happens? One is 10 and the other one is negative 10. One is 4, the other one is negative 4. So I get the opposite of A comma B. And that is a y-axis reflection. The way you're going to see the notation here, they're going to use capital, I think they use capital R. Just pay attention in your homework, the first couple of sections here. They might use a capital R, and then down here, like y-axis, they might say capital R and write x-axis. Capital R stands for reflection, and then obviously this tells me over the line that I'm going to reflect. You might see it lowercase as well, so lowercase r and then y-axis, lowercase r, x-axis. Either one of those is possible. Okay. There are some other lines that we reflect over. I'll just kind of demonstrate this here in GeoGebra, and I'll just do it with 1 point. Okay, so I'm going to put the line y equals x in here. And throw a point up. Okay, so if I want to reflect across that line, what's going to happen is that we want the distance from this point to that line now to be the same. Well, how do we measure distance from that point to that line? We do it with perpendicular segments. So what I'm going to do, just to demonstrate this real quick, I'm going to go with a line from here, perpendicular to there. Okay. If I find the intersection of that line and that one is B, so now I'm going to remove this line and just talk about this segment here. Okay. That, well, it's supposed to be blue. There we go. That blue segment, we know it's perpendicular because I just made it. I used the perpendicular tool. So that's the distance. That 4.24 is the distance that A is from that red line. When we choose this object to reflect, it says we can reflect about a line. So I'm going to take A, point A, and we'll reflect it about the red line. Let's see here. A, about that line. For some reason, it's not. There we go. So A, reflected about that line. There we go. We get A prime. Okay. Now, what I want to do here is just talk about the distance that A prime is from the red line. So if I look at this segment right here, that black one, let's make it that color. Okay. You see that purple line is the same as the blue one. So that means that A's distance from the line and A prime's distance from the line is the same. So distance is preserved. Okay. If you look at A's point 5 comma negative 1 and A prime's point negative 1 comma 5, there's a relationship there. Okay. So now no matter where I move A, so the way I built this should move A prime as a reflection. You see when it goes 6 comma 1 and then 1 comma 6. Here we've got 9 comma 2. Do we have 2 comma 9? 6 comma 3, 3 comma 6. Okay. So if you think about this, this is something we've already done before. If you remember, we talked about when a point is equidistant, or when a point falls on the perpendicular bisector of a segment. Say my segment is A prime to A. That point B is the same distance from A prime as it is from A. Now a lot of times we didn't use B. You might have seen instead put the point there, and we said A prime to C is the same as A to C, which would be true, but it is also true right there when A prime to C is the same as C to A. So there's some relationships to what we saw. I think it was when we talked about chapter 4 with end centers and circumcenters and all that kind of stuff. So what's the rule here? The rule is when we reflect across the line y equals x, so you'll see it written this way, reflection across the line y equals x of A comma B, what that generates, okay, if you started with, if that's my A and that's my B, doesn't it become B comma A? Don't they flip? So if I had, 5 comma 4 on my pre-image, then I now would have 4 comma 5 on my image. And that's reflecting across the line y equals x. Same thing really happens if I go across the line y equals negative x. Let's see here. There's a line y equals negative x. Let's just take, we'll just do this quickly. Take a point like 1, 4. And if I reflect 1, 4 across that line y equals negative x, you see that they flipped again, but now they both become negative. So that's the rule when we do a reflection across the line y equals negative x. If you started with a point A comma B, like 1, 4, it turns into the opposite of B comma the opposite of A. So you flip them both and you negate them both. And that's going to give you a new point on your reflection. Something that some people struggle with in the homework is what happens when we reflect a point like not over those lines, but it's over like this line. Like say, let's take the line x equals 3. And I have like that point right there, 6 comma 5. And I want to reflect it across the line x equals 3. So we'll go reflect across the line x equals 3. The point A, so you might see it written this way. And then I got to find what A's coordinates are. They're 6 comma 5. Or you might see it written reflect across the line x equals 3. The point 6, 5. What is that going to become? Well, remember, distance is preserved. So the ones you're going to see the most part in this section, you can do some pretty easy counting here. But what happens is that line right there, and you're going to reflect over vertical or horizontal lines, so it should be pretty easy. That is a distance of 3. So when you reflect, that reflection distance should also be 3. So A is going to go right there, and that's going to call it A prime. So now 6, 5 reflected over line x equals 3 is going to become, is going to become the point 0 comma 5. If you think about what we did here, and we'll maybe do another one here. Let's go the point, let's just go x equals 3 again. The point, let's go 8, 2, and see where that gets reflected to. So all I've got to do is move this point down here to 8, 2, and we'll reflect over that line. So then that distance right there would be 5. So then I got to reflect that 5 again over here. So that distance would be 5. So now 8, 2 is going to become negative 2, 2. Okay. So let's kind of talk about this real quick. How do I get that? How do I do this a little bit quicker algebraically? Well, if you think about it, what we were subtracting from, so when I started A being right there, we started with that 6. And when A prime went there, I got eventually 0. That was the x value was 0. So I took that 6 and I had to subtract 6 from it to get 0. Well, where does the 6 that I subtract from come from? It's that distance there. But that distance is found by taking that number minus that number. Would have given me 3. Now I know a lot of them are 3's here, but 6 minus the reflection line gives me 3. Okay, let's just call that distance C for the moment. If I double C, so make it 2C, that is actually what I subtracted from 6. So here's just a general rule here. If I'm reflecting over a vertical line, okay, a point A comma B, it is going to become A minus 2C comma B, where C is found by taking the A coordinate minus the reflection or the line of reflection. So let's see if that pattern there, and you can do this with a lot of stuff. Obviously this is a tool to use if like this number was like 600 and I want to reflect over the line negative 450. I don't want to have to count those things. I want to have a formula that generates it for me quickly. So in your homework you should be able to count. Shouldn't be a big deal, but if anything like this were to materialize, this is how you would do it. So let's see if this rule here gets this point negative 2, 2 from 8, 2. So what we said, we started with 8, 2. Okay. Now I want to figure out what the C distance is. So that C distance is found by taking the A value, which is 8, and subtracting from it that number 3. So it gives me 5. Okay. So it does generate that little distance right there. I want to double that 5 to get this 2C. So I'll take 8 minus 2 times that 5, and then comma B, which is still 2. So that's 8 minus 10, which is negative 2, left with a y value of 2. So it's kind of a quick way to work through a reflection across a line that is not the line y equals x or x-axis, y-axis, and so forth. You can do the same thing with a vertical reflection. So you'd be reflecting over a horizontal line. It'd be a vertical reflection because the image is moving up or down in the planes. But this thing here, all that would happen is that you would have like an A, comma, and then your y value would be B minus 2C, because that is what's changing with a horizontal reflection, or sorry, a vertical reflection. When you reflect over a horizontal line, the y values are what change, not the x's. Okay, so give those. There's going to be a homework assignment here with Math Excel. Give it a shot. If you have any questions, let me know. One thing I want you to remember here, just run through these real quick again. If I'm going to do a reflection over the x-axis, okay, of a point A comma B, it's going to become, so over the x-axis, the y changes. So it's going to become that. If I go reflection over the y-axis of a point A comma B, so it's the x that changes, so negative A comma B. If I'm going to go reflection of the y equals x line of A comma B, that the order pair is flip-flop, B comma A. If I go over the line y equals negative x, then I start with AB, it's going to become negative B, negative A. And let's go just say, reflect over like Y equals, I'll call it C here, of A comma B. Actually, I don't want Y, I want, apologies, we go X equals C of A comma B. The algebra of it is that it's going to be A minus, actually let's not call this C, let's call it D. So it'd be A minus 2C comma B, but remember how I found C. C was found by taking your A coordinate and subtracting D from it. Okay. And you might even just be so it's a distance. Doesn't matter the order that you do that subtraction, make it the absolute value. And it'll make things a little bit clearer for you. And if I want to go over, so the same thing happens then when I want to go like Y equals D of A comma B, then it's going to be A, but now it'd be B minus 2C, where again C is equal now to what would be your B value that you started with, be the B value minus that D that you're reflecting across. Those are, like I said, these are not necessities. They are not 100% needed. A lot of the questions that you're going to be doing are small enough to where you can count. If I were to throw one in that you can't count, this is maybe the structure that you would use. Okay, I'm not saying you have to memorize these. You can by all means draw a quick sketch and kind of figure things out that way. But those would be useful. So translations, reflections, both isometries. The next time we meet, I will talk about rotations and dilations. Okay, and those will be, I'll give you some rules for those things as well. Not too bad.